Hi, everyone, and welcome back to Psych 3530. What we are going to go over in this lecture is the statistical sort of extension of part 2 of chapter 10 on within subjects experiments. So, what we're going to do today is called a dependent samples. You often hear it called a paired samples t-test. And this is the test that we use when our experimental design has a single group of people who we test multiple times. So we have a single group of people, and maybe we follow them over time, and we do a pre-test and a post-test. Or we have a single group of people, and we're going to put them in two experimental treatment conditions and then compare those treatment conditions. So the key here is that we use a dependent t-test in situations where we have one group of people and we are collecting data from them twice on the same dependent variable. So let's go over those again one more time. We can basically divide these situations when we use a dependent t-test into longitudinal designs and then what we're going to call repeated measures designs. Now, a longitudinal design is technically a repeated measures design, but for the sake of sort of some distinction here, we're gonna separate them such that a longitudinal design is one in which we design an experiment where we follow people over time. Now, this time can be a few hours, it can be a day, it can be years, but we're following people over time in this sort of before being compared to after sort of situation. So an example of an experimental design that we would call longitudinal might be that we give a bunch of high school juniors and seniors, we give them the SAT, and we see what their score is. Then we enroll them all in a prep course for maybe a month. They take the prep course, and then we give them the SAT again after the prep course. So we have time one, and then we have some intervention. This is a very common format for a longitudinal design is intervention studies. We measure them at time one, we have some intervention, and then we measure them at time two on the same outcome, in this case, SAT. Now, longitudinal designs can also just be change over time with age. So we measure maybe anxiety symptoms in 15-year-olds, and then we wait for 2 years, and we measure anxiety symptoms in those same children now at the age of 17. We follow them for 2 years. So in that case, there's not really an intervention. It's just we're following them over time. Age is kind of the intervention, if you will. But these are designs where we follow people over some period of time versus a repeated measures design where we're taking one group of people and we're exposing them to multiple treatment conditions in quick succession. So we're not following them over a week or 2 weeks or 2 years. We're bringing them into the lab and we're putting them in situation one and we're measuring something. And then we're putting them in situation two and we're measuring that same thing. And we're going to compare those two treatments together. Now, this feels a lot like a between subjects design, except we're using the same subjects in treatment one and treatment two. So the group of people is being compared to themselves. That's what makes this within subjects, rather than being compared to an entirely different group of people, which is a between subjects experiment. So I want you to imagine that we're interested in how cell phone usage impacts driving errors. So we bring 50 people into the lab. We have a driving simulator. We have them go through a driving simulator using a cell phone, and we record all their errors. And then we have them go through, the same people go through the simulator without a cell phone, and we record all their errors. So we have exposed them to two treatment conditions, cell phone and no cell phone, in quick succession. And then we're going to compare their performance across those two treatment conditions. So in either of these situations, and these are the more common ones that you will see, in either of these situations, we need what's called a dependent t-test. A good way to remember that why we call this a dependent t-test is because the scores are dependent upon one another because it's the same people, right? Your after score is, in a sense, dependent upon your before score because it's the same group of people. So think about it that way. Okay, here are our steps all the way through a dependent t-test. We're going to define populations and hypotheses. We're going to do some math. Then we're going to find our critical value. We're going to make a decision. And then we're going to write our APA-style conclusion. So what I'm going to do is walk you through each of these steps, giving you some explanation as to what it is and why we do it this way, and leading all the way, just like our independent t-test, to an APA-style conclusion. So let's do an example. You're interested in how therapy impacts depressive symptoms. So our research question is, does depression decrease over time with 2 weeks of therapy? Does depression decrease over time with 2 weeks of therapy? So you collect data from 6 participants. You measure their depression before therapy. We then send them to therapy for 2 weeks, and then we measure their depression after 2 weeks of therapy. So here we have a longitudinal within subjects design. We can see that we end up with our 6 participants and their pre and post test scores on depression, such that every row represents a different individual. And so we have 2 scores per person, pre and post. We're going to assume alpha equals 0.05. So the first thing we need to do is define our populations and hypotheses. So restate your problem in these terms. So we want to make population 1 and population 2 basically depressed people before therapy and depressed people after 2 weeks of therapy, right? That's who we're doing the study on, right? People with depression before therapy, people with depression after therapy. The kind of weird thing is that population 1 and 2 are the same people, right? We follow them over time, but sort of in the way that we're setting up our decision making, the question we're asking is, do people differ before therapy versus people after therapy? So we kind of have 2 populations, even though in our study, these populations are technically the same people. So our hypothesis is that depressives who receive intensive therapy will see a decrease in their depression scores. Our null hypothesis is that they will not decrease in their depression scores. So we can express our hypotheses with these inequalities. I think sometimes it's easier to start out with the research hypothesis. So people before therapy, right, population 1, this is mu, so it basically means the average of population 1. They'll have more depression, right, greater depression than population 2, which is people after therapy, right? So depression will decrease, meaning that before therapy, we'll have more depression than after therapy. And the null hypothesis is just everything else, right? Every other possibility, which is encapsulated by this inequality that they would be less than or equal to. So the first thing we're going to do is calculate a change score, because what we're really interested in here is change over time. or a difference score. So you'll probably hear and see me call this either a change score or a difference score. You can see that up here. They're really just interchangeable terms, right? Change score from pre to post, or a difference score between pre and post. Same thing. What's really important when we calculate this score is that this is going to become the data that we use. We're actually going to drop these data. The actual raw data that we collected aren't the data that we actually do math on. We do math on these change scores because the change score is what we're actually interested in. I don't actually care about the level of depression pre-therapy. I care about the change in depression from pre-therapy to post-therapy. A crucial and critical piece of this is that when we calculate this change score, we always want to do post minus pre, or after minus before. Because when you do the math this way to get the difference between the two scores, the sign of your change score for each individual reflects the actual direction of the change. So notice participant A. Prior to therapy, they scored a 26 on our measure of depression. After therapy, they scored a 15. So they decreased their depression by 11 points. So we do 15 minus 26, which gives me negative 11. And this negative 11 reflects an actual sort of negative decrease, right? They decreased in depression, so we end up with a negative change score. Imagine if we did pre minus post. So this person, we would flip these two numbers, and their math would be 26 minus 15, which would give us a positive 11, which the math will all work out. It would be okay. It's just confusing because now this person has a positive change score. It's counterintuitive because they actually decreased, right? So what we would prefer is to keep things less confusing. So we do post minus pre, such that their change scores reflect the nature of their actual change. So we calculate a change score for each participant, and then we find the average change score for our data. Here, the average change score is negative 4.33. So on average, therapy decreased depressive symptoms by 4.33 points. The next thing we need to do is find the sum of squares, variance, and standard deviation of this change score. So we do our sum of squares table again. We take each individual change score. Remember, we're working with the change scores, not the raw data anymore. We take the mean of these change scores, and then we take X, which is our individual scores, minus this mean. So negative 11 minus negative 4.33. Be careful because the signs matter. Don't drop the negatives here, right? This person had a negative change score. The mean for these 6 people is a negative change score. So make sure you're doing negative 11 minus negative 4.33. Be very careful with your calculator here. And that produces our difference score, right? Because subtracting a negative is the same thing as adding, right? So the number we go from 11, and we have a difference of negative 6.67. 0 minus negative 4.33 should actually be 4.33. Sorry about that. I made a mistake with my calculator. Negative 3 minus negative 4.33, right? We got back on the right track there. So on and so forth. Excuse me. Where we get our difference scores for our change scores. I'll obviously change that in the static PowerPoints for you. Sorry. So change score minus mean gives us our difference score. We then square each difference score. and we add them all up to get our sum of squares, 83.34. So now we want to find the variance of those change scores. Variance, which we denote as s squared, is just sum of squares divided by n minus 1. So 83.34 divided by, we had 6 participants. This is important because even though we started with 12 data points, right, 2 data points per participant, n is not the number of data points, n is the number of participants. So we had 6 participants. So 6 minus 1 is 5. 83.34 divided by 5 gives us a variance of our sample of 16.67. We should go ahead and calculate the standard deviation of this sample, which is just the square root of the variance. So we pull this number, our variance, and we just take its square root. So the square root of 16.67 is 4.08. That's the standard deviation of our change score. Now we will use this standard deviation if we need to calculate an effect size, and we will use it in our APA style conclusion. But this number is not what we carry forward for the t-test. We can go ahead and find it now, but for right now, we're going to set it aside. We're going to ignore this 4.08 because that's not actually what we need for the t-test. To move forward with the t-test, we need to carry over the variance, 16.67. So the next thing we do is we use the variance of our sample to estimate the variance of the population and then estimate the standard deviation of that population, which we call the standard error of the mean. Now, if you remember our discussion of the distribution of the means from our independent t-test, that's the same thing here. We're making an assumption, right? We're using the data we have as a sample to estimate what the sort of typical amount of error variability would be in a distribution of the mean for these data. So we have 2 simple formulas for that. The variance of M, the variance of the distribution of the mean, which we take our variance from our sum of squares table, 16.67, and we divide by n, not n minus 1. We divide by n. So 16.67 divided by 6 gives me 2.78. We're just pulling over our variance and dividing by n. Then we're taking the variance of our distribution of the mean, and we're taking the square root of it because we want the standard deviation of the distribution of the mean, the S sub m. So we take the square root of 2.78, which is going to give us 1.67, and this guy is going to be the denominator of our t-test. So that's the math. The math is easy, right? You find your sum of squares, divide by n minus 1 to get a variance, 16.67. Divide by n to get the variance of the distribution of the mean, as opposed to the sample variance, which is 16.67. And then we use the variance of the distribution of the mean to give me the standard deviation of the distribution of the mean. 1.67 becomes the denominator of my t-test. So that's the math, but let's talk for just a second again about the theory behind this. What 1.67 represents is the amount of random error or variability that I should expect at the population level in people's depression scores across 2 weeks. So I use my sample data to estimate how much just from random day-to-day fluctuations might people's depressive symptoms vary randomly, because we want to beat that random error. We're wondering, does 2 weeks of therapy change people's depression scores more than people's depression scores would change just randomly in the natural world? This 1.67 is an estimate of that error. It's an estimate of how much people's depression will randomly fluctuate across time. And so we're going to compare our change scores to this random error variability by calculating a t-value. Here's your formula for a dependent t-test. M is our mean change score. So that was negative 4.33 in this case. Our mean change score minus mu. Mu is the mean of the distribution of the mean. What's important here is for you to know that in a dependent t-test, this value is always 0. Always. Every time and twice on Sundays. It's always 0. Why? Because we're comparing the change that we observed in 2 weeks of therapy, M, against the idea that nothing happened, right? It's kind of our null hypothesis, right? Mu ends up being our null hypothesis because we assume that therapy did nothing. If therapy did nothing, then what would our change scores be? They'd be 0. So we start with the assumption that nothing happened, 0. And we compare our observation against that assumption of 0. That's what our numerator is. We observed a decrease of 4.33 in depressive symptoms, and we're going to compare that to the idea that therapy did nothing, right? 0. That's why the mean of the distribution of the means is always 0. Now, that's our numerator. And then we divide by the standard deviation of the distribution of means from the previous page, our 1.67. So we end up with negative 4.33 minus 0 divided by our standard deviation 1.67 gives us a observed t-value of negative 2.59. But we need to know, is that extreme, right? Is that a significant t-value? So we need to find our critical t-value. We need 3 pieces of information. We need our total degrees of freedom, which is 5. Remember, we had 6 participants. Minus 1 is 5. Alpha, which was given to us in the problem, is 0.05. And we had a one-tailed hypothesis because we were wondering if depression scores decrease with therapy. So we made a specific directional hypothesis. So we know we're on this row because we have 5 degrees of freedom. We have a one-tailed test with an alpha of 0.05, so we know we're in this column. And so our critical t-value is 2.015. We need to put a negative sign in front of it because we made a negative one-tailed hypothesis. So our critical t is negative 2.015. So we can call that our cutoff t-value, right? Our line in the sand. Our observed t-score from our sample is negative 2.59. We are more extreme than the cutoff value. Thus, we reject the null, and we're going to end up concluding that, yes, in fact, therapy does decrease depression. Let's look at that on our distribution. So our critical t-value, our line in the sand, was negative 2.015. So if we're more extreme than that, then we reject the null and we conclude that therapy works. So we are more extreme. The change that therapy enacted in depression was an extreme enough change above and beyond what we would consider typical. Thus, we conclude that therapy works. Therapy does something. Therapy does actually enact change on depression. So we reject the null. The null is the idea that it doesn't do anything. So we reject that idea and we support the research hypothesis. Because we're significant, we need an effect size. It's Cohen's d again. It's very similar to our independent t-test in that the numerator is still the same. So the mean change score minus mu, which is always 0. So we have the same numerator as our t-test. And then we divide by that standard deviation that we had earlier, right? We divide by s. Earlier, we calculated s squared to be 16.67. That's the variance of our sample. We took the square root of it, if you remember, to get our standard deviation of 4.08 of our sample. And so we just plug that into the denominator. Negative 4.33 minus 0 divided by 4.08 gives me a d of 1.06. Remember, we want to interpret the absolute value of effect sizes. Their directionality doesn't matter because we already have information on the directionality of the effect from our t-test. Effect sizes, Cohen's d, is a measurement of how large the effect is, so we can just ignore its directionality for interpretation. So we get a d of 1.06. If you remember back to our discussion of interpreting Cohen's d, anything over 0.8 is considered large. So here we have a large, robust effect. Here are all the steps, all the math at least laid out. So before you get to here, right, you need to calculate a sum of squares. So you do your change score, you do your sum of squares table, and then you follow these formulas in turn. These will be available to you for the exam, so don't worry about memorizing them. And lastly, we need our APA-style conclusion. So, a dependent samples t-test was conducted to examine whether depressives who receive intensive therapy decrease in depression scores. That's our introduction of our test and the introduction of our research question and hypothesis. As predicted, after, that says 6 months. That should say 2 weeks. My bad. I'll change that again. As predicted, after 2 weeks of therapy, patients' depression scores decreased significantly. Mean equals negative 4.33. Standard deviation equals 4.08. T, 5 degrees of freedom, equals negative 2.59. P is less than 0.05. D equals 1.06, one-tailed. Therefore, therapy is an effective treatment for depression. So we provide our test, we provide our research question, we provide our the results of our statistics, both the descriptive stats and the inferential stats, and then we provide a take-home message. So the last 2 slides of this lecture are 2 practice problems that you have. Use the steps that we just went through here to try and complete both of these practice problems. Try to do it without looking at the answers, although the answers to these practice problems will obviously be posted on iCollege for you to check your work. So take a crack at them, see how you can do following these steps all on your own, and then look at the at my voiceover video that will walk you through the answers and see hopefully what you got right, and if you made any mistakes, where you went wrong. So thanks, everybody. And I will see you, or I'm sorry, I will talk to you later when we go over these practice problems. So thanks, have a good one, and good luck on the practice problems.